Hey, it's time for section 15.2 about exponential and logistic models. So in this section, we're not going to really be doing anything new. We're just going to take the things that we learned about in the last section and apply them to kind of dealing with some like story problem situations. So we're going to start by defining like our general exponential model here. Now I know that the terminology refers to everything as populations, but like the population can just be like final amount and initial amount or whatever. It doesn't have to refer to like living organisms or whatever. We're not talking about necessarily populations like that. It could be, you could talk about money or like, weights of something or whatever. But this is just like a general exponential model. So P of t represents like our final amount, or like the amount that we're looking for, some future value. P sub 0 is the initial population, or the initial amount. That's like whatever our starting value is. R is the rate of growth written as a percentage, or it could be rate of decay, depending on the phrasing in the problem. So R is going to be written straight as a percentage, and it would be positive for if things are increasing and negative if things are decreasing. So that's going to help indicate whether we're doing growth or decay, because whether things are getting, the population should be growing or shrinking. And then t is just our unit of time. So that time could be days or months or years, but in most situations it's usually like some fixed amount of time. A lot of times it would be years. So I just want to point out to you that this is still really our exponential form, y equals a times b to the x, where a is just p sub 0. 1 plus r over 100 is really just our b. And then obviously t is just x, and p of t is just my y. Right, so this is still just describing an exponential function. It's the same description that we saw before. We've just written it a little bit a little bit funny. The one thing that's worth pointing out here is that this initial population has to be a positive number. If we're talking about things, real life objects, it doesn't make any sense to let that thing be negative. Where when we defined our exponential in general, the a we said could be really anything that was non-zero. So that's what we mean there. Okay. So the next example here, we're going to talk about just looking at one of these exponential models and trying to decide whether they're growth or decay, and then afterwards finding the rate of growth or decay. So remember that to determine this, we really just need to look at the value for b, the base of the exponential. So here the b is 1.0384. And since that's greater than 1, we know that this is growth. Now to solve for r, what I'm going to do is I'm going to say, okay, well I know 1 plus r over 100 has to equal this value for b. Oops. 1.0384. So when I subtract 1 from both, I get 0.384. And when I multiply both sides by 100, I get 3.84. And r is written as a percentage. And again, we notice that that's a positive value, which kind of matches up with the idea that this is going to be growth. If I look at the second example, here we have that the b is 0.9867. And since that's less than 1, we know that this is a decay. So since it's decay, this is 1 plus r over 100. Nothing really changes because it's a decay. So I'll start by subtracting 1 from both sides. And here things change a little bit because I get negative 0.0133. Notice I'm getting a negative number here. And when I multiply by 100, I get negative 1.33%. Again, I'm getting a negative number here, which syncs up very much with this being a decay function. So that's like all we need to do for that kind of a problem. To determine if it's growth or decay, we just look at whether the b value is bigger than 1 or less than 1. And then to find that rate of growth or decay, we just set the b equal to 1 plus r over 100 and solve for r. And that's it. It's pretty easy. So next example, we're just going to write a population model. So we're going to just write the equation. So we want a population model with initial value of 15, increasing at a constant rate of 6% every year. So we're going to be using our population model that we gave at the beginning. So we're told the initial value is 15, so that's my value for P. And we told the rate of change is 6% for R, and since it's increasing, we know that this is positive. So let's go ahead and fill those in. And then if I do 1 plus 6 over 100, that turns into 1.06. And there's my final answer. That's it. Again, and since this is worth noting that since our rate is happening every year, our time t needs to match that unit, so t would be in years for this model. In general, when trying to determine what unit t is, that unit should match the population. So what would this, how would we change this if it was, instead of happening every year, it was happening every 6 months? So let's look at the exact same problem, except importantly, instead of this happening every year, we have this change happening every 6 months. So again, we'll be using the same population model. And just like before, the value for the initial value, still 15. The rate is still 6%. But now we have to think about t. So there's two options here. We can do t is equal to years, or we can do t being equal to months. We can't do t equal to 6 months. That's not allowed. T needs to be like some fixed unit of time, like some normal unit of time. Actually, let's write this way. And because we're going to go and look at two different options. So if we're measuring t in years, how many times does 6 months go into a year? Twice. So instead of t, we're going to write 2t. So our model then would be, P of t equals 15 times 1.06 to the 2t. So every year we get 2 of those 6% increases because that 6% increase is happening every 6 months. So that should happen twice inside of 1 year. What if we measure the time in months instead? Well, 6 months happens 1/6 in a month, right? So 6 months doesn't happen in a month, right? That's silly, but 6 months is 1/6, or 1 month is 1/6 of that time interval. So all I'm going to do is t is going to turn into t over 6. So p of t equals 15 times 1.06 to the t over 6. Depending on whether you want to measure t in months or t in years. In general, the way that this works is if the time interval that we get the change occurring in is less than the time interval for t, you're going to end up with a coefficient. If that time interval that the change is occurring is bigger than the interval or the time unit that we're measuring t in, it's going to create a divisor. Okay, so that's the easy way to remember it. So if t, the unit that t is bigger than the unit for the rate of change, the time unit for the rate of change, then you're going to get a coefficient. If not, you're going to get a divisor. So let's look at another example. Okay, so it says suppose a colony of bacteria is put in a petri dish and the culture doubles every 3 hours. Predict how long it would take for there to be 400,000 bacteria. So again, we're going to start by writing our model. And should be easy to see that our initial value for P is 120. But here we're not given a percentage, right? What is the change happening? We're told that culture of bacteria doubles every 3 hours. So let's worry about this doubling part here. What that's saying here is this whole value 1 plus r over 100 should really just be 2. Okay, so we'll deal with that in a second. Before we do that, though, we should pick our value for t. So I would say, since this is happening every 3 hours, let's say t is measured in hours. And since 1 hour is less than 3 hours, I'm going to be getting a coefficient, or I'm sorry, a divisor. So we'll write t over 3. So let's put this all together now. So P of t is 120 times 2 to the t over 3. Okay. So now, if I want to find out how long it's going to take for there to be 400,000, I'm going to do this problem with my calculator. So I'm going to get rid of all this mumbo jumbo I had here. Go in and clear all this stuff out. And I'm going to type in my model into my first spot. And again, I'm just going to use X's instead of T's. And then my next spot is going to be 400,000. So that's a 4 with 5 zeros after it. And now I need to change my window. So I don't know how long this is going to take, right? It's doubling every 3 hours. I don't know. I'm just going to pick 100 hours, and if it needs to get bigger, I can always go and make it bigger. The minimum amount of bacteria is the 120. Since that's relatively small, I'll just go ahead and do that. And then I need a maximum number of 400,000, so I'm going to just pick some round number bigger than that. I'm going to pick 500,000 for my y's. And then I'm going to hit graph. So there's my bacteria curve. Woof, that is steep. So there it happens way in before 100 hours. Kind of surprising. So to find the point of intersection, I press second and trace. I'm going to select the intersect command. And then again, we just have 2 curves and 1 intersection, so I can just press enter 3 times. And it says that intersection is at 35.11. So how would I answer this? I would say in about, or maybe we should say just over 35 hours, the bacteria population will be 400,000. Yikes! Get out the bleach. Another very common application for exponential modeling is radioactive decay. So some of you, if you've had a chemistry class or maybe even an earth science class, have talked about this. Radioactive decay is the process in which the number of atoms for a radioactive substance change from a radioactive state to a non-radioactive state. Each element on the periodic table does this in a fixed amount per given unit time. The half-life of a radioactive substance is the time that it takes for exactly half of a radioactive substance to become non-radioactive. So let's look at an example problem on kind of how we interpret this and build out using our exponential model. So suppose that the half-life of a certain radioactive substance is 35 days, and you have 10 grams of the substance initially. Find the time it would take for there to be only 1 gram remaining. So we'll just use our normal exponential model. And hopefully it's easy to see that because we have 10 grams initially, that's our P of 0. But maybe it's not entirely clear what the value for R is. Since it's a half-life, it's decay, so it's negative, and half of 100 is 50. So that's my value for R. For all these radioactive decay problems, the R is going to be negative 50. So that makes life easy to remember. And then we need to pick a unit of time for T. I think day seems appropriate. Again, it matches the unit here. And since 35 days is bigger than 1 day, I know I'm going to end up with a divisor on my T. Or this just simplifies down to 10 times 0.5 t to the 35. And to figure out when there's only 1 gram remaining, I'm going to use my calculator. So very similar setup as to last time. So here I'm going to have 10 times 0.5 to the x divided by 35. And then this is going to be 1. Oops, 1. So change our window. Again, it's time, so we'll take, we know time is going to start with 0. And if we think about this in our head, 1 half-life is going to go from 10 to 5. That's 35 days. A second half-life is going to go from 5 to 2.5. That's another 35 days. 2.5 goes to like 1.25. That's another 35 days. And then somewhere in between that and the next time is going to cross from 1.25 down to 1. So I know we need at least between 3 and 4 half-lives. So 4 half-lives is 140. So I'll do that as my maximum x. Oops, 140. Again, writing down what I just kind of thought through. We have 10 grams at 0 time. We have 5 grams at 35 days because it just cuts it in half. We have 2.5 grams at 70 days because we did another 35. We have 1.25 at 105 days. And then after another 35 days, that would be cut in half. So that would be like 0.625. So somewhere in between here is when we're crossing down to 1 gram. That's what I'm looking for. But I just kind of did that quickly in my head to get a good idea of the X max. So I'm just counting half-lives basically to figure out how many days, my upper bound could be, just so I can get this graph to come out on the first shot. The X minimum, well, if we're decaying, the least amount of stuff you can have is 0. The maximum is 10. That's how much we started with. Notice that when we're doing a decay problem, the initial is the end, is the maximum. The initial amount, the amount we start with, is the maximum because we're getting less each time. And the minimum would be 0 because, again, you can't get less than like 0 of something, right? You can't decay down less than 0. And now we're ready to hit graph. So there's my half-life curve. And there's my line at 1. So my intersection is happening there. So I'll press second and trace, choose the intersect command. And then again, we have only 2 curves that we graphed and only 1 intersection from those 2 curves. So I can just press enter 3 times. So I get 116.27. And let's go back and read how they wanted the answer. Find the time it would take for there only 1 gram to be remaining. So 116.27 days would be fine, or just over 116 days. That would be okay. Anything like that would be okay. So our last example we're going to look at, a logistic situation. So let's take a moment and look at that. Okay. So this question says you start a bunny petting zoo. You determine the population of bunnies on your farm can be modeled by the equation B of t equals 800 divided by 1 plus 99 e to the negative 0.5 t, where t is measured in years. So we ask first, how many bunnies do we have initially? So initially is when time is equal to 0. So what we want then is b of 0. That's 800 over 1 plus 99 e to the negative 0.05 times 0. So that's going to give me 1 plus 99 times e to the 0. And if you remember, anything to the 0 power is just 1. So that can just kind of cancel out. So I'm left with 800 over 100, or 8 bunnies initially. Alternatively, you could do this on your calculator. So if I press alpha and y equals, it gives me that fraction options. I'll take the first one, and I'll just do 800 over 1 plus 99 times e to the negative 0.5 times 0. And I get 8 that way also. So either way. Okay. The next question asks, what is the maximum sustainable population of bunnies on your farm? So if you remember, for logistic growth or decay, we have 2 horizontal asymptotes. So we said the limit as x approaches positive infinity of b of t is going to be c, and the limit as x approaches negative infinity of b of t is going to be 0. So this is going to be the upper bound for it. Remember, if we think about our graph, we have like an asymptote here and an asymptote here, and we're going to end up with like this S-shaped graph. So like this amount here is like our upper bound, the most bunnies we can get. So in this case, what is our C? It's the numerator. That's it. Pretty easy, if you know what you're looking for anyways. And then it asks, how long will it take for you to have 500 bunnies? Well, we're going to do this graphically. So the first thing I'm going to do is type in the logistic model into y1. So 800 over 1 plus 99 times e to the negative 0.5 t, and again I'm using x instead of t, and then my second equation is just 500. So reset our window. So if I think about this, I don't really have a good intuition about you know, how fast this bunny population is growing, but we're starting with 8. Bunnies breed pretty fast. I don't know. I'm going to just say 20 years. Maybe it's more, maybe it's less. I'm not sure. If I have to, I'll go back and check. And I know that my logistic curve is bounded by 0 and c. So I'll just do 0 and c for my y min and y max. And then I'll hit graph. So here's my logistic curve, that nice classic S shape. And there's 400 that comes right on through. So I'm going to just look for this point of intersection. So second trace, intersect command. I have only 2 curves and 1 intersection, so I can just press enter 3 times. And I get about 10.21 years. So to go from 8 bunnies to 500 bunnies, little more than 10 years. Wowzer! I hope you like bunnies. But that's it for this lesson. At this point, you guys are ready to do homework problems from 17 up into 36. So good luck with that stuff, and we'll see you in the next lesson.